Okay, success. It's finished 100%. It took almost 10 minutes, so it wasn't exactly zippy, but it was very easy to do. Let's have a look. We have precisely 400 chunks. I've run this a few times. I don't always get precisely 400 chunks. I think it's a coincidence, but there we go. That's nice. Although it was slow, it was very easy. And that was step 2. Step 3, you remember, is just to save these embeddings. So we're no longer using LangChain, so we're now just calling Chroma direct. And it turns out that's pretty easy. We just call the database like this. Chroma is persistent client. This is the same as before. If the collection exists, delete it. And then we're going to get all of the texts, chunk.pageContent for chunk in chunks that collects all the texts. We will create embeddings by calling openai.embeddings.create. It's nice. Now we're doing the code ourselves rather than just going through like the retriever. We very clearly separate the database from the encoding. So this is where we are clearly calling OpenAI to turn this into vectors, and we collect those vectors. And then in Chroma, we've got our collection. We now simply add to the collection the vectors, the texts, and the metadata, and it's done. That would be the create embeddings function, calling the encoder and calling Chroma direct, no longer LangChain gluing them together. And now we run that, off it goes. It's now going to Chroma. It's putting 400 vectors in there, and it's been done. The vectors have been created. We've got 400 vectors in Chroma, and well, I guess that's it. Then we can go home. Or can we go home? Have we forgotten? Have I forgotten something? I'm not talking about actually doing the question answering. Of course, we also have to do that. But before any of this, we don't know that these 400 vectors are in Chroma. We don't know they're there unless we can visualize them. So it turns out it's basically exactly the same code as we had before. We do the same thing to gather the vectors, the documents, the metadatas, and make colors. And then we use t-SNE just as we did before. t-SNE, do you remember what it stands for? T, distributed stochastic neighbor embedding. We use t-SNE to reduce it down to 2 dimensions and plot it in a picture. Here it is. I love these pictures. And that's pretty nice. We've got a nice cluster of greens, a nice cluster of yellows. We've got the blues. They do seem around here to get sort of stuck into the contracts, but it does appear to be the features. Look at that, features and capabilities. It's the features part of the contracts that are more over here with the products. But it is interesting that products and contracts do seem to be like on each other like that. But it's still very cleanly separated. I'd say that visually looks like a good improvement over even what we had before. And now we will bring it up in 3D because, you know, that's just the kind of person I am. Up we come. We can swivel around and, oh, it's just so great. What could be better than this? You could just leave me now. You could fast forward the video like an hour and see me still going, so spend the time, you know, enjoy browsing around this vector space. But this is the difference, of course, keep in mind, is that now each dot, the 400 dots, don't just represent taking a document and like striking them in various places. But we've used an LLM to decide how to divide them into chunks. And we've also written little summaries associated with each one. That's what we've added to the mix to make it something that's going to be really good at answering questions. So that is success in our vector data store. That is the ingest part of it. And now we move on to the retrieval, the question answering part of this, the answer. So we're going to do some re-ranking. That's very trendy. And we're going to do some query rewriting as well to mix with our document rewriting. Okay, so first of all, we're going to create another pydantic object, another object called rank order, which is something which is quite simply a list of integers. That's all it is, called order, a list of ints. And it is the order of relevance of chunks from most relevant to least relevant by chunk ID number. That's what this is. That's a new class called rank order. And why do we have that? Because we want to write a function called re-rank. And again, this is another chance for you to see a simple function, which is making an LLM call packaged together now. We're going to make a prompt, put it into messages in the OpenAI style, and then we're going to use Light LLM, but you could directly use a call to an API, to a model to carry out an action. And again, I'm going to use structured outputs. I'm sowing quite a lot of seeds here on this. I was thinking I'd just give you a hint on it, but you're basically learning structured outputs. We're doing that as well. So the system prompt, you are a document re-ranker. You're provided with a question and a list of relevant chunks. The chunks are provided in the order they were retrieved. It should be approximately by relevance, but you may be able to do better. You must rank the provided chunks by relevance to the question, most relevant first, reply only with a list of ranked chunk IDs, nothing else. And then that's the system prompt. The user prompt, the user is asked the following question, order all the chunks. Here are the chunks. And then I list out the chunks with a chunk ID. And then that goes into messages with the system prompt and the user prompt. This is the system prompt. This is the user prompt. I know you get it. And then finally, we call Light LLM. We call completion, the same as openai.chat.completions.create. We call completion. We pass in the model. We pass in these messages that I just created right here. And here, this response format. This is structured outputs. This is where I say you have to reply in this format. It's told that it has to create JSON that meets this spec. And so then we get response.choices0.message.content, and we turn that into a rank order object. And what I can do, I can just add in here print order. I'll print that out so you see what it looks like. And then this is just some fancy Python. This is Pythonic. This is the equivalent. This is like saying, okay, so let's say result is an empty list. And for I in order, look at cursor filling in, result.append, that we could build up the result and then return results. Return results like that. Thank you, cursor. But all of this that you see right there can be done in a fancy list comprehension like that. And as NumPy people who are here would know, with NumPy, you could use like a super fancy slice thing, which would be really nifty. But this is pretty good. So there you have it. This is going to print the order and then return the chunks reordered. So first of all, let's just have a simple fetch function, fetch context unranked. Let's not re-rank them yet. So this is basically the alternative, not using LangChain, just doing retrieval ourselves. And we're just going to, first of all, you remember with LangChain, we've got a retriever object, and we call the retriever object invoke, retriever.invoke, and it just does everything for us, but it's not clear like what's the embedding model and what's Chroma. Here we get to do everything nice and cleanly separately. Step one, we do openai.embeddings.create with the question. The question comes in, we turn it into a query. Okay. Step two, we go to Chroma, we query the collection, given this query, and we say that we want K results. That is our retrieval. And then finally, we are going to then come in and collect the documents and metadatas, and then we're going to return those chunks. We're going to append that to a collection called chunks, a list called chunks. Okay, so let's see this at work. I've got it right here. So we've got a question. Who won the IIoTY award? Do you remember who won the IIoT award? Maxine won the IIoT award. Let's see what happens if we do a fetch context unranked. So it's turning it into a vector. It's then retrieving it from Chroma and coming back with the top chunks like this. So that all happened. And I just printed out. Let's print a little bit more than that. You can see we've got a bunch of different documents that have come out related to this. Here they all are. Let's now we'll come back to that second question. Hang on. Let's now re-rank this. Let's come in and say re-ranked is re-rank of this question and these chunks. So we're calling this re-rank function right here. We're calling that re-rank with the question again, and with the chunks, the unranked unre-ranked chunks that we just got. Okay, let's run this. Okay, it's re-ranked them, and this is the order it re-ranked them in. The same first one, and then 4, 3. The chunk number 2 came right down at the end. Let's print this out and see how it looks. For chunk in re-ranked. So here we go. You can see that career advancement is still the first one that came, but the second one is other HR notes. That came up to the top there. And I'm expecting that probably these two are the two that mentioned the IIoTY award. Well, there we go. Let's do another one. I have got a hard question, a trap, a nasty question that I slipped in there, which is that I made Jessica Yu, I think she's called. Jessica Yu has deep down in her HR record that she went to the University of Manchester. And we are going to now ask a difficult question about who went to Manchester University. And we're going to retrieve 20 documents from the database. And if you try this question on the prior version from a couple of days ago, you'll find that it can't get the right answer from yesterday. Go and give it a try. If you've still got that running, and I hope you do because we're about to make it better, try on asking who went to Manchester University and it will tell you, I don't know. So now we're going to dig into that and do some re-ranking with it.